what I did, I was looking at, was I looking at 16? I was having, I kind of felt that I wasn't communicating what needed to be done, and that was either on 16 or 18. What, do you remember which one we were? On page 117. I'll take a look at 16. Is it possible for a 5 by 5 matrix to be invertible when the columns do not span R? So what we have, A is a 5 by 5. 5 by 5 does not span R5. Then if you look at theorem 8H, that particular theorem is negated because it says, let's see, let's see. So if A does not span R, then theorem 8H is negated. Therefore, you can say A is not invertible because if theorem 8H is negated, theorem 8A is negated. Because if you look at theorem 8, it says the important thing is in that sentence at the top. It says either all are true or all are false. So if one part is false, then every other part is false. Well, 5 by 5 does not span R says that theorem 8H, the columns of A span R, is negated. It's not true. And if theorem 8H is not true, then every one of those other elements is not true. And that means that theorem 8A is not true. A is not invertible. So that they're either all true or they're all false. So that's how you would prove that particular thing. On 18, it's saying C is a 6 by 6, and the equation Cx equal V is consistent for every V in R. So C 6 by 6 and Cx equals V is consistent. For every V in R. And then you could say by definition, that's a mixture of words. A consistent system is at least one solution. Then theorem 8G, and notice 8G says the equation AX equal B has at least one solution for each B and R. That's G is met for C. Then that means that C is invertible by theorem 8A. And then C has a unique solution and this is theorem 5, and that's on page 106. Therefore, you can say Cx equals V cannot have more than one solution. So that's the way you go through proving, showing that that statement is true. Okay, 20, it says E and F, see, if n by n, so E and F are n by n matrices. This is what's given for you. And E, F equals I. And then what you can say, E and F are invertible. And if you look at in the box, bottom, page 114. Notice that in the very bottom of that brown box it says A and B be square matrices if AB equals I, then AB are both invertible with B equals A inverse and A equals B inverse. So they're both invertible. And E equals F inverse and F equals E inverse. Therefore you can say that FE equals I equals E F. All these questions are just proof questions. (24) says L is n by n, and then so the given part L n by and Lx equals 0 as trivial solution. Okay. And then theorem 8a d, excuse me, is met. And if you look at theorem 8d, it says the equation, the homogeneous equation ax equals 0 has only the trivial solution. So that's what that would say. And then what you could say is L spans Rn, because if theorem 8d is true, then theorem 8h is true. Yeah.
Well, problem set, and this is 24, it only says that it has a solution. All matrices have a trivial solution to their x. Theorem states that it only has a trivial solution for x equals 0.
No, the homogeneous equation can have non-trivial solutions. But this one says that the homogeneous equation, this homogeneous equation has the trivial solution.
I thought all homogeneous equations have trivial solutions.
No. They can have non-trivials. Is there a certain place that...
I was just thinking it would be all the trivial solution because taking the matrix equals 0 is kind of trivial to say, well, that was 0, that all variables equals 0. So I was just going to say...
If when you try to reduce the matrix, if you have a row that does not have a turning point in it, pivot point, yeah, then it will have a non-trivial solution.
Okay.
You can have a homogeneous equation that when you try to do reduced echelon or echelon it, that it'll have not a
I was just noticing the slight distinction here because the
Yeah.
it says the only solution is trivial. Just this one states it has one that isn't excluding non-trivial solutions. So there's a distinction. Ariel, we're talking to just notice this difference.
Yeah. Yeah. Well, if it doesn't have a turning point, I always say turning point. What is it? Pivot point. If it doesn't have a pivot point, when you go and try to reduce it, then the homogeneous equation will not have a trivial solution. But here it's saying that and you see that D says the equation AX equals 0 has only the trivial solution. So if all homogeneous, just think about this, if all homogeneous equations had only the trivial solution, then this wouldn't be written in the theorem. I mean, I'm trying to go by counterpoint, right? See, because it would be redundant. If all homogeneous equations had only the trivial solution, then a theorem wouldn't include that as part of a statement that would then go if and only if other stuff. Does that make sense? So if it's using that, then the homogeneous has to have the possibility of having a non-trivial solution. Does that make, without going back and finding where it says it? You have to say, well, they wouldn't put that in there. Does that make sense? Okay.
Sorry.
No, that's good. That's good. I'm glad I'm able to answer it. This isn't my field of expertise. This is, and then, it has, what you have to do with this courses like this, and which is, you referred to what the algebra, it's all based upon definitions, theorems, postulates, and all that. You got to remember all those things to be able to prove, things, and that's tedious. That's theoretical mathematics, which is, I got out of that a long time ago. Now I have to teach it. But fortunately, it's not a 400 or 500 level. It's a I think this is a 300 level, or is this 2x? I would pull my hair out if I teach anything higher than this. I think I'm teaching this because nobody else wants to teach it. And I'm the new guy. They say, you get to teach it. Okay, explain why the columns of A2 span Rn whenever the columns are linearly independent. So what we're given is that the columns of A are linearly independent, right? So, because that's true, then theorem 8e is met. Notice 8e says the columns of A form a linearly independent set. All right. And what we're trying to do is that the columns A2 span R2. So then if you go down to theorem 8H, because theorem 8E is met, then that says all of those other ones are met, and theorem 8H says the columns of A span R. So we can say, therefore, the columns of A2 span R2, and that's by theorem 8H. Does that make sense? I mean, does the logic of it make sense? What's that? Which one? That therefore the columns of A2 span. This is supposed to be span R2, and if you look at theorem 8H, it says the columns of A2 span R2. And the reason that you can say that is because their given statement is the statement of theorem 8E, right? What's given to you is what theorem 8E says, right? So, and theorem 8 says that if one of those is true, then all of them are true. So then you can go down and say, well, theorem 8.8 has to be true, which says that it spans it. Does that logic make sense? That's how the logic goes. You're taking the given statement and then trying to work it around so that you get something in the theorem and that you can go to the statement that makes what your conclusion is true. Okay. 28. It says show okay. I'm gonna you can see what it says. So what I'm going to say is I'm going to say it this way. I want to say what's given to us. In the problem, it's given that AB is invertible. Right? And they want us to prove then that, and so if AB is invertible, then so is B. So this is the given statement. If AB is invertible, then you can say theorem 8A, AB is a matrix, right? And so by theorem 8A, AB is invertible. So if you think about it, that AB is just this matrix, not A, not B, just AB is the matrix. And this meets theorem 8A. And then if 8A is met, then what you can do is you can go down to theorem 8J, and you can say, well, then there's got to be a W. So there's this a matrix W such that W times AB equals I. And that's theorem 8J. Does that make you're treating AB as if it's a single matrix. So you could say, well, you could just substitute. You could just say AB. I'm going to think of it as C, matrix C. Well, then theorem 8A says C is invertible. So then there's got to be this W that when I multiply it times C, which is actually AB, gives me I. That makes sense? Then what you can say, W A B equals I. And this is theorem 2A. And if you look back at theorem 2A, do you see that? Do you see it? It says A times BC, then it's AB equals this theorem is saying this. If you got A times BC, then you can write this as AB times C. Associative property. Okay. And that's equal to I. Then this says then theorem 8J is met, and therefore B is invertible. theorem 8A. That makes sense. I'll do one more. $30. So if A is an n by n matrix and the transformation x transforms into AX is 1-to-1, what else can you say about the transformation? So what's given to us? A is n by n. And transformation is 1-to-1. Then what this is 1-to-1. Then this is actually theorem 8F is met. Notice that theorem 8F is saying the linear transformation A transformed into AX is 1-to-1. So they're giving us that. So now we're in the theorem 8, so everything else in 8 is going to be true. Then they're saying what else about that transformation? What else can you say about this transformation? Well, if you look in theorem 8, it's saying that F that I is the linear transformation A to AX maps Rn onto Rn. So the first thing is that the transformation X onto AX maps Rn onto Rn. So that's the first statement we can say that is true because the transformation is 1-to-1. Then its transformation is onto. Now, because A is invertible, that's theorem 8A, then 2, the translation X AX is invertible. And this is theorem 9. So you can make these two statements because you're given this particular thing. Okay. Now, what the next section on 2.4, they're going to talk about. I started. What time did this class start? 8:30. Okay. They're going to talk about partitioning the matrix. And notice that they're in that example 1, they partitioned the matrix into essentially submatrix. And what they're calling it block matrices. And that's just the partitioning of a matrix. So then what you're going to do is you're going to have a new matrix that's going to be a group of matrices, partition matrices. And the matrices don't have to be the same size. You just partition it off. And notice that they're doing that matrix A, and they're doing matrices in those different categories. If you look on 120, there's under multiplication of partition matrices. It says partition matrices can be multiplied by the usual row column rule as if the block entries were scalars, provided that for each product AB, the column partition of A matrices and the row partition of B. So all they're saying is that when you can multiply, as long as when you're multiplying, that the size of the matrix matches the multiplication. In other words, if you're multiplying this partition matrix, and you multiply the partition up here, its columns have to match the rows in this other partition matrix. Otherwise, you can't do the multiplication. That's all that they're saying. And notice that they're talking about conformable matrices for block multiplication. And then they're someplace in there they're saying, the reason that you'd partition a matrix is because the size of the matrix. If the size of the matrix gets so big that it's unwieldy to handle, you can partition it down so that when you're doing the blocks, that it becomes easier to deal with. So let's look at theorem 10. It says the column row expansion of AB. It says if A is M by N and B is N by P, then AB, you're doing those columns and then the row. And they're just saying that the column rows will come out just as if it's scalars in those positions. Inverses of partition matrix. If you have that on page 122, you have a matrix and then you have its invert. It's got to get the partition matrix that you arrive with as a multiplication solution has got to have the identity matrix in the diagonal for each of the partition matrices. I guess we'll just look at some problems. Page 123. And 1 through 9 says, assume that the matrices are partitioned conformably for block multiplication. Compute the products shown in exercises 1 through 4. So we have E0 and 0F. So what we can do with this is we just multiply that one times this one. And then we put it up in there. So EA plus 0 times C. It isn't because my hand is so shaky, but this thing must be terrible sensitive. And then E B plus 0 times D. And then 0 times A plus F times C. And then 0 times A F times D. So then the upper left is EA, and it's EB, and FC, and FD. I guess pretty straightforward multiplication, right? Okay, look at 4. I 0 minus X. IA plus 0C. That's IB plus 0D. That's minus XA plus IC. I don't have room to put that bracket up there. So this is IA, that's IB, that's minus XA plus C, because I times C is C, XB plus D. So ultimately it's A, B, it's A, X, I got XA plus minus XB. Okay, if I did my multiplication right, that's what it should be. Now, 5 through 8, it says find the formulas for X, Y, and Z in terms of A, B, and C. Justify your calculations. In some cases, you may need to make assumptions about the size of the matrix in order to produce the formula. It says compute the product on the left and set it equal to the right side. Okay. This gets pretty long. Six. X0. And it does no good to try to clean it up. X0. Y, C. Zero. That's equal to I, 0, I. So what we do is we're just going to multiply this out. The left-hand side. Did I have this written right? Is this, no, 6, okay. So this is XA plus 0B. And that's A0 plus 0C. And that's YA plus ZB. And then it's Y0 plus ZC. So this is XA. This is 0. And then YA. Z. Okay, so then we have XA equals I. That's putting these two together. And this is theorem 8J is met. Therefore, theorem 8A is invertible. And X has to equal A inverse. That's that box on page 114. And we're supposed to get, what? Find the formulas X, Y, Z in terms of ABC. So then what we can do is we can do X, A invert equals I, A invert. And then there's that theorem that says I can do X social property. And then this is A invert. X, this is I. So X is equal to A invert. And now what I've done is I've shown X in terms of A. It says find the formulas X, Y, and Z in terms of A. So I've got X in terms of A. Now, if we look at this, look at this thing right here. It's showing that YA plus ZB equals 0. And then we can subtract things from both sides. So YA equals a negative ZB. But now I've jumped the gun. I want to do something else first. Is it okay if I erase this? Okay. We'll come back to this later. But I need to show something else first. I'll leave it there. Dang it. Let me get this back. Okay. I need to show this first. I need to show that ZC equals I. And that's theorem 8K is met. Then C, it implies C is invertible. Theorem 8A. And then for the same reason we can say Z equals C invert. I'll just put C above. Now then, I can take this thing and go on with it. So that's true. But now Z equals C inverse. So what I have is YA equals a negative C inverse B. And A as shown as invertible. YA A inverse equals a negative C inverse B A inverse. But then you can do A inverse. YI. So Y equals negative C invert B A invert. And so this is showing Y in terms of ABC. This is showing Z in terms of ABC. Well, jeez. I must have jumped back up a slide, didn't I? Did I lose something? I guess not down far enough. Where did my thing go? What? Is it this one? It's this one. Somehow it changed places. But you see, we've got everything like it said it wanted. It wanted all the X, Y's, Z's in terms of ABC. There's one of them. Here's the second one. And there's the third one. Okay. I'm going to quit. Because if I do another one, the next one's going to be longer. What? No quiz.
Minutes.
I think, I don't know what I told you at the beginning. I worked long and hard to get 4 tests graded so everybody could have their stuff back before you went on break. Because I know I would have been upset if I had waited till after break to get my test back. So, you can appreciate it or not, I don't care. But my theory is I get stuff back to you as quick as I can. I put in some night hours to do it. So.